In this video, I will define two new concepts, monotonic sequence and bounded sequence. Then I will explain how these two concepts relate to whether a sequence is convergent or divergent. Let's begin with monotonic sequences. This is going to require a few definitions, not just one. I say that the sequence AN is increasing when every term is smaller than the next. This is equivalent to asking that for every two indices, n and m, if n is smaller than m, then a sub n is smaller than a sub m. These two conditions are equivalent. The second condition should be familiar. It is how we defined increasing function if we are talking about a function with domain the reals, for example. But for sequences, we get the two versions and they are equivalent. We often use the first one because it is simpler. For example, the sequence n squared is increasing. Similarly, we can define decreasing. It means that every term is greater than the next. I could also write the second equivalent version of this definition. For example, the sequence 1 over n plus 1 is decreasing. I have used strict inequalities to define increasing and decreasing. I can also define the equivalent concepts with non-strict inequalities. I will call a sequence non-decreasing when every term is less than or equal to the next, and non-increasing when every term is greater than or equal to the next. For example, the sequence 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and so on is non-decreasing. Notice that every increasing sequence is also non-decreasing, but the converse is not true. And finally, I say that the sequence is monotonic when it is any of the above. Monotonic is an umbrella term. When working with examples, we often use induction to prove that the sequence is monotonic, but if the sequence comes from a function, there are other ways. Let's look at an example. I'm looking at the sequence n cubed times e to the minus n, starting at 0. And I want to know whether it is monotonic. This sequence comes from a function with domain all the real numbers. I can define the function f by the equation f of x equals e to the minus x times x cubed. And this sequence is simply the function f restricted to the naturals. Now, if I want to study the monotonicity of the function, I will probably look at its derivative. After computing and factoring, the derivative f prime equals this expression. The derivative is negative for all values of x greater than 3, therefore f is decreasing on the interval from 3 inclusive to infinity. This is what the graph looks like. What about the sequence? Well, the sequence is almost decreasing. The same sequence, but beginning at n equals 3 is decreasing. In this situation, I am going to say that the original sequence is eventually decreasing. Here is a precise definition. A sequence is eventually decreasing when every term is greater than the next one, but only starting at some fixed index n sub 0. Of course, we have similar definitions for eventually increasing, eventually monotonic, and so on. That was the first concept, monotonic sequences. Let's move on to the second, bounded sequences. This is not a new concept. The definition of bounded sequence is the same as bounded function. I say that a sequence is bounded below when there is a real number that is less than or equal to all the terms at once. I say that the sequence is bounded above when there is a real number that is greater than or equal to all the terms at once. And I say that the sequence is bounded when it is both bounded below and bounded above. That's it. Important observation. It is not worth it to define eventually bounded. Nobody uses this concept. Can you see why? The best way to get comfortable with these concepts is to try to construct examples. At this moment, I invite you to pause the video and try to come up with 8 examples of sequences for each combination of bounded or not bounded, monotonic or not monotonic, and convergent or divergent. Try to do this exercise before you continue watching to avoid spoilers. Have you tried? If so, you probably noticed that some of the examples seemed impossible. Indeed they are. There are 3 important theorems that summarize all the restrictions we have. I will introduce them now. First, if a sequence is convergent, then it must be bounded. This is theorem 1. Second, is the converse true? If a sequence is bounded, can I conclude that it is convergent? In general, no, but with an extra condition, yes. If a sequence is monotonic and bounded, then it must be convergent. This is theorem 2. Actually, we do not even need to require monotonic. It is enough to require eventually monotonic. This is a fundamental principle that illustrates why the notion of eventually is important. To determine whether a sequence is convergent or not, only the tail of the sequence matters. Changing the first 2, the first 10, or the first 300 elements won't affect whether the sequence is convergent or not. Therefore, if the theorem works with the hypothesis the sequence is monotonic, then it must also work with the hypothesis the sequence is eventually monotonic. It cannot possibly matter whether the first 15 terms are out of order, for example. This theorem is very important and it has a name. It is called the monotone convergence theorem, and I will add 4 sequences to the name because there are a few other theorems called monotone convergence theorem in other areas of analysis. Sometimes the theorem is not stated precisely like this. Sometimes, instead of talking about monotonic sequences, we look at increasing and decreasing sequences separately, and we write 2 separate theorems. We can say that if a sequence is eventually increasing and bounded above, then it is convergent. And on the other hand, if a sequence is eventually decreasing and bounded below, then it is also convergent. If you look up monotone convergence theorem in books or websites, you will probably find these 2 statements instead of the one I wrote earlier. To be precise, we do not even need to ask for a strict monotonicity. We could substitute non-decreasing and non-increasing for increasing and decreasing, and the theorems could still be true. In summary, when we say the monotone convergence theorem for sequences, we are referring to any and all of these versions. They are all true. Back to the 3 theorems. I am still missing one. According to theorem 2, if a sequence is increasing and bounded above, then it is convergent. What happens if it is increasing and not bounded above? Then it must be divergent to infinity. And that's it. Those are all the 3 important results. Theorem 2 and 3 together tell us that the behavior of an increasing sequence is very restricted. Here's what I mean. In general, a sequence may be convergent or divergent. And if it is divergent, it may be divergent to infinity, to minus infinity, or divergent in a different way. For lack of a better term, I will call this divergent oscillating. However, according to theorems 2 and 3, an increasing sequence may only be convergent if it is bounded above, or divergent to infinity if it isn't bounded above. This will become very useful later when we talk about series. And this is the end of the video. In the next 2 videos, I will write proofs for theorems 1 and 2. After you watch them, I invite you to try to use the same ideas and write a rigorous proof for theorem 3 as well.